Hi, welcome back to Practical Skills for Making Stuff with Electronics. I'm Tyler Bletch with Duke University. This is the second part of our two-part series. This video covers connectivity, the human interface, and fabrication techniques. If you want to jump to a specific subsection, you can find timestamp links in the description. Remember, the prerequisite to these videos is that you already know the basics of electronics, and you're wanting to learn how to integrate electronics into larger projects, to understand the design space of options out there to build things, and to learn some practical advice to avoid the most basic mistakes so you can build a variety of electronics-based projects. If we come back to our map of a thing, in the previous video we discussed sensors, digital modules, and actuators, and in this video we're going to cover everything else. The connectivity, physically, how do we wire these things, the human interface, and the physical enclosure, frame, chassis, whatever mechanical thing you're building to realize your project. Let's start with the human interface aspect. If you want to make a human interface, you're going to need some kind of inputs. Now, we've learned many of these already. We've learned about buttons and switches. Humans can press those. We've learned about potentiometers, which a human can think of as a volume knob. We've learned about mechanical rotary encoders, a clicky selector knob to go through a menu, for instance. But we're also going to touch on a few other things, including joysticks and touchpads. We're going to cover these sensors in the context of how do we physically build these in a way that a human can interface with easily. There's also human outputs, LEDs, displays of various kinds to tell the person what's going on with the device. We also have to discuss how we're going to put this thing together, this interface aspect together. I divide your options into three categories: hacky nonsense, printed circuit board mounted techniques, and panel mount techniques. Let's start with the simplest, hacky nonsense. There's nothing truly wrong about hacky nonsense. What I mean by this is maybe using a breadboard as your interface, so you just have to see the buttons right on there. There's lights just stabbed right into there. It's fast, it's good for prototyping, but it's a little fragile and it doesn't look real nice. It's hard to make a breadboard-based interface look nice. We could do other stuff. We could like hot glue buttons to things and have little wires running off that people can see, and that kind of stuff can be okay in a pinch. But it turns out it's not that hard to make a fairly professional-looking interface. So these kind of techniques are fine when you're testing things, fine on your workbench, but I wouldn't give it to a customer. Now, if we want to move past our hacky nonsense, we could go all the way to the other extreme, printed circuit boards or PCBs. This is how real industrial products are built, and we'll get into printed circuit boards in more detail later on, but right now I'll just say they're a flat substrate where we route copper to other things so we can connect stuff together. You can build your interface using a custom printed circuit board. That's how game pads are built, for example. But if you're relatively new to electronics projects, it's probably not where you should start. Printed circuit boards are great, but they're really complicated to get right. They require really tight tolerances, complex tools. However, it turns out there's a nice way for the hobbyist or new project engineer to get into making good-looking interfaces, and that is panel mount devices. Panel mount is a general term. You can include this in your searches for various kinds of components. That basically means you're going to put a hole in some kind of flat panel of metal or plastic, and then this device, maybe a button or a switch or anything else, will slide in there and either click in place or be held on with a nut or some other kind of connection mechanism. And when you're done, you're left with a really clean-looking professional interface. And you might not know it, but you've seen these things in a lot of places. Panel mount buttons, panel mount switches and toggles, an entire arcade machine, like an arcade cabinet. All those controls are panel mount. You can buy arcade buttons and drill a hole and put them in your project. You've probably seen little LED indicator lights on the surface of a panel. You can have panel mount LED. You can have panel mount ports. Think of like the power port on small consumer electronics. Oftentimes that's drilled as a hole. The port itself is stuck in there, and there's wires in the back that run to the circuit board. If you've ever used a benchtop power supply, like you might find in any kind of electronics lab, those ports that you plug the power cables into, are panel mount. You can buy them yourself and integrate them into your project. You can even buy panel mount displays. All kinds of things come in this panel mount form factor because it allows people to make interfaces and other devices that look professional, but are still easy to assemble without complex tooling. So let's get hands-on and look at a practical example of a simple panel mount interface. So here we have our servo demo from earlier, and let's say we want to make this into a bit more of a professional enclosure so we can use this servo tester in the future. Let's make note of our inputs, controls, and outputs. As an input, we have a power coming into it via USB here. There's a little notch cut out for that. For our output, we have the servo wire sticking out here. And for our interface, we have a potentiometer, which is actually a panel mount potentiometer. So we can take this other piece of a cardboard box here, and I've already cut corresponding notches, a hole, and a hole here. We can run our cable out the back here. And I'll point out this zip tie here. This zip tie will serve as strain relief. We'll talk about this a bit later, but basically it's going to prevent people from being able to yank this wire out of the box. Pull that wire here, take our potentiometer, and feed it through a hole in the front. There. Put the whole thing together. And now we can just attach the included washer and nut. Tighten that down. That's good enough for now. And we can even put on this nice knob. So now we have a nice professional looking enclosure. We can connect the servo, this wire here. We can apply power from USB. And we have fine-grained control of a servo with a nicely mounted knob. Panel mount controls. Now I mentioned LEDs in the context of panel mount, but LEDs or light emitting diodes are useful for all kinds of things, and they come in a lot of useful form factors. You've probably already seen individual LEDs that you might put into a breadboard, but if you're making larger interfaces, art projects, anything like that, you can look at other form factors, including LED strip. This is a flexible tape filled with LEDs that you can light up either in one color, multiple colors, or even have each LED be a different color. The simplest form is called an analog LED strip. This is where it's just LEDs in a row and power lines. The only tweak on top of this is you might have what's called RGB or red, green, blue LEDs, meaning that each actual LED is 3 colors that you can choose from, and by mixing these colors you can make pretty much any visible color you want. In an analog strip, you have power lines for the red, green, and blue channels, so the whole strip will always be the same color. If you want to get a little fancier, you can look at digital LED strip. This is where each LED is actually a tiny little computer. It's pretty crazy. We're in the future. Where you can send a digital message along the LED strip telling each individual light what color to be. So now you can have rainbow LED strip. Typically the backside of this is some kind of adhesive, so you can stick this around your project. And there's multiple flavors to research and multiple ways to interface with these things. There's even 2-dimensional LED matrices. So you can have simple ones that are just one color controlled by some simple controller chips. And there's even more sophisticated, larger full-color ones intended for large-scale digital signage that you can get an interface with to make full-color patterns. Now, if you want a more practical display, you could look at either LCDs, liquid crystal displays, or organic LED, OLED displays. There's some common options shown here. A common Nokia model, a common text model, and then a smaller OLED model. All 3 of these can be interfaced with electronics using ready off-the-shelf libraries and tutorials. If you need a full-color or interactive display, there are various models of touchscreen you can interface with your Arduino, Raspberry Pi, or other microcontroller. One nice trick if you're making some kind of game or something similar to that, is to interface existing off-the-shelf peripherals like joysticks. Now, the one thing you probably don't want to go for is USB. USB is complicated. It's for full-scale computers. It's not super easy to interface with that. One thing that is easy to interface with is the older, what are called game port joysticks. You can still find these used floating around thrift shops and eBay, where literally the movement of the stick is just analog pins and the pressing of buttons is simple on-off signals. You can also interface with older video game console gear without too much trouble. It depends on the specific thing, but for instance, Nintendo and Super Nintendo controllers are very easy to interface with. The Nintendo Wii accessories for like the nunchuck have a simple I2C protocol that you can talk with. And there's lots of other console stuff that can work. Just Google it. If you Google Arduino and then any video game console accessory, you'll either find a tutorial saying how to do it or someone sad that it's not easy to interface with. And then you'll have your answer. So now we have all these panel mount controls, we have a joystick, we have all these things. How do we hook it all together? And that question, how do we hook it together, can really be divided into two questions. There's the electronics engineering question of what wire goes where, and that I'm going to say is out of scope for this video. You should be researching videos and tutorials for your specific use case as to how to connect things up. What I want to talk about is physically, how do we best make those connections in such a way that they won't break, they'll be reliable, and we'll know what's going where. It's an often overlooked question, but it's important because the most common thing for a new electronics project engineer to run into is they've built the thing, it works, they go to show someone, and the wire breaks off, or it becomes flaky, or it doesn't turn on because of a simple mistake. So let's talk about techniques to physically fabricate the electronics, the connections. The simplest technique to connect things together is called point-to-point. That is, I know this piece of metal needs to be touching that piece of metal, so I'll run a wire between them. You do that enough times, you can make any circuit. But as you can see in the pictures on the right, it gets crazy really, really fast. Point-to-point is good for simpler things. For panel mount electronics, for panel mount interfaces, it's the way to do it, because all your components are spread out by definition. But for the actual integrated circuit components, it can get too crazy. So let's look at another technique, breadboards and protoboards. So as I mentioned at the top, you should already be familiar with breadboards at a high level, how you can connect things together, plug them in, what connects to what. These work great for prototyping, but they don't hold up well. You could do the hacky thing and kind of hot glue your stuff into the breadboard and pray, but even that doesn't last too long. Stuff gets in there. It's not meant for long-term construction. If you want something to be reliable, you want to solder it together. But as we saw in point-to-point, you don't want to just solder wires to everything. That goes crazy. So we'll turn to our friend protoboard. Protoboard is a series of holes on a printed circuit board with the same spacing as a breadboard. And there's various flavors of this stuff. You can get one where it's literally just the holes and nothing is connected other than just you can put things there. You can also get flavors where there are copper traces between the holes in certain patterns. One common case is they make protoboards that have connections that are exactly like the connections on a breadboard, such that if you make it work on the breadboard and then you move everything to the exact same spot on the protoboard and solder it together, it will work. So there's many flavors of this. If you're building one of these on protoboard, whether or not it's the fancy pre-connected one or just a plain bunch of holes or one of the other flavors, at some point you'll get to a situation where you want two things to be connected that aren't already connected. If they are neighbors, that is, they're right next to each other, you just kind of blob the solder between them. If they are further apart, you take a piece of wire, connect it right next to the two things so that the ends of the wire are neighbors to the things you want to touch, and drag solder across those. This technique of dragging solder to connect neighbors is called drag soldering, and you can find lots of good tutorials online on doing that. As you can see in the picture in the bottom middle here, you can build fairly complex circuits on a protoboard just by running wires for your interconnect. The kind of wire you want to reach for here is 22 gauge solid core. We'll talk about wire selection a bit later in the video in detail, but in the context of this kind of design, 22 solid is the one you want to go with. Now let's say you're sick of fiddling with the little proto board stuff. It's annoying to bend all the wires and figure out where it's going to go. You might want a printed circuit board or PCB. This is, again, a flat substrate with just lines of copper to various spots to connect a circuit together. Once you have a printed circuit board, let's say someone handed you one, you put your components on the board, you solder them together, you trim the excess leads off them, and you get a finished circuit. It's nice, but where do the printed circuit boards come from? Well, the printed circuit board itself is a substrate of a non-conductive material, typically some kind of fiberglass, with a plate of copper on top that has been etched or carved out to leave behind the traces or connections that we want to have. On top of that, we put what's called solder mask. That's what makes the printed circuit board green or whatever color it is. It's an insulator, electrical insulator. And then maybe there might be some text on top, typically in white. This is called the silk screen. It gives us labels as to where to put things. Now, how do you make a printed circuit board? Well, that is a whole process. I'll give you the short version here so you can start your research if you want to go down this path. You'll have some kind of electronic design automation software to help you design these things. Common choices are Eagle, which is free for hobbyists and nonprofit people. There's KiCad, which is a newer open source electronics design package. And there's also really expensive, fancy industry tools like Altium. Whichever one you want to pick, you can find lots of tutorials and resources online. I'll give you a picture of the high-level workflow here. First, you'll start not in the software at all. You'll design your circuit kind of with breadboarding, simulation, prototyping. You'll figure out what you want to build and how it's connected. Once you know that, you'll have the schematic, a logical diagram that says what is connected to what, without worrying about how the copper is going to look. Once you have your high-level schematic, you put that into the electronic design software, and then you press one button and it flips it over from schematic view to board layout. And it says, well, your schematic says these things are connected in this way. Here's their layout on a circuit board. Move it around. Move these pieces around as you see fit. Through either your action or automatic action of the software, decide where to lay the copper in order to make the connections that you want to make. Then lastly, that'll give you a board layout that you can either fabricate at a facility. For instance, if you're at Duke on campus, there's machines that can do this in the CoLab. Or you could send it out to be manufactured. The easiest way to do that is to go to a site called PCBshopper.com. You tell them what kind of board you want to make. They price compare all the board fabricators, and you just pick the one that's cheapest and fast enough for what you're doing. And they will ship you those boards pre-made, and you can solder your thing together. PCB design is a little complicated, takes a fair bit of practice. I wouldn't recommend it for your first, second, or maybe even third project. But once you get more used to the basics of electronics, it's a great resource to reach towards to simplify your design experience. So whether you're using proto board or printed circuit board or point-to-point, whatever you're doing, you'll need to use wire to connect your stuff together. So let's talk about some basics of understanding wire. First, wire thickness is commonly measured in American wire gauge or AWG. This is because it's an American standard like pounds and feet, it's going to be weird. Lower numbers mean thicker. Don't ask me why. The most common numbers you might want to see are, as I mentioned before, 22 AWG is your most common breadboard wire for basic electronic stuff. 18 AWG is what you'd find on the laptop charger. 14 AWG you'd see on a lamp cord or basic like a simple appliance cord. And then 10 AWG is what you see on a really beefy extension cord. It's intended for like construction. You're hooking saws up to it and stuff. The reason why we have these different thicknesses is that thicker wire can carry more current without getting too hot. You should also be aware of wire material, but the good news here is that copper is the only real answer. There's aluminum wire for certain weird applications, but you generally don't see it. In general, if it's normal electronics wire, even if it looks silvery, it's probably copper because they will plate copper wire with other metals to reduce oxidation. Wire also comes in two forms, two physical forms. There's solid core, that is, it's literally just a beam of metal in an insulation. And then there's also stranded, where instead of a single thing of metal, there's many, many fine hairs of metal together in the insulation. Solid core is simpler, it's easier to work with, but it can break. It's subject to what's called metal fatigue. Imagine taking a paperclip and bending it back and forth over and over. Before too long, it's going to break, and you won't have a paperclip anymore. The same thing is true of solid core wire. Stranded wire doesn't have this problem. The individual strands can flex and move between each other, so it is far less subject to metal fatigue breaking. In fact, most of the wires that you find around society are in fact stranded wires for that reason. That said, I'll give you a simple rule on picking wire form. If your wire is 22 gauge or thinner, and it's not going to move very much, solid is the easier thing to pick. For all other cases, go with stranded. If it's going to move at all, or if it's going to be thick at all, or both, stranded is what you want. So let's dig a little deeper and look at the various packages that wires can come in. The simplest form of electronics is called hookup wire or primary wire, and it's the most basic kind of wire you can think of. It's just a wire with some insulation on it. A single conductor, and it's either typically PVC or silicone insulation, and it's good for whatever you want to do. Primary wire is fine. If you find yourself needing two conductors together, most commonly to provide power and ground, you want to look at either zip wire or speaker wire. These are two conductors, typically stranded, where the insulation is joined together but can be torn apart like a piece of paper. This is nice for power because it stays as two conductors the entire way. Then at the very end, when you're tapping it for power or hooking up to a connector or something, you can split just a little bit off and solder it or connect it to whatever it needs to go to. If you need more than two conductors, you might want to look at jacketed wire. Jacketed wire is actually the really common form of wire you see around in society because it's when you have two or more conductors, each of which is insulated with an outer envelope outside. USB cable is all jacketed. Ethernet cable is all jacketed. Phone cable is all jacketed. And how it works is you'll split off that jacket, and then you can separate the individual conductors to hook them however you want. Another form of multi-conductor cable that's useful is ribbon cable. Ribbon cable is nice because it comes in wide, flat arrays. It can be multicolored, so you can tell which color is doing which purpose. You can tear it in the same way as zip wire to make any smaller size ribbon cable you want, and you can even crimp on various kinds of connectors relatively easily. This is commonly used within an electronics project because it's a bit more fragile than jacketed wire, but it's easier to work with in terms of connecting it to many different things. Lastly, I should point out there is such a thing as called magnet wire or transformer wire. It looks like bare copper in most cases, but it's actually coated in a very thin layer of transparent enamel that makes it insulated. This is what they use to make the windings inside of motors and transformers and stuff. You probably don't need to work with it, but you should be aware that it exists. So how do you mess with wire? It's pretty simple. You cut it with a wire cutter, you strip it with a wire stripper. There's two main flavors of wire stripper. They have strengths and weaknesses. I have both on my bench. There's the classic wire stripper where there's little holes for each wire gauge, and you figure out what gauge you have, and you cut it very, very precisely with that. There's also the auto stripper, which I actually use the most. You just lay the wire in sideways, kerchunk it, and the insulation comes off real fast. It takes a little getting used to, but it's real fast. If you get an auto stripper, get a nice one. The cheap ones are garbage and don't work at all. One side tip, if you're messing with wire, if you have many separate individual wires and they're gonna go along the same path, and you want to kind of bond them together, a simple cheap trick is take the ends of the wire, put them in the end of a drill, hold the other end, and run the drill, and it'll twist all the wires together into a really nice looking braid that you can then run wherever you want. So now that we have wire, we probably need connectors, the plugs that hook things together. There's many, many, many connectors in our world. I'm going to give you the most commonly useful ones for a new electronics engineer. The most common one you're going to see starting out are these DuPont pins. If you've learned anything about Arduino, you've probably seen these things. These are when you have either little pins sticking out or little holes for pins to go in with these black plastic housings. These are nice because they can plug straight into an Arduino, into a breadboard, into the what are called the headers on many printed circuit boards. Headers are either those female ports shown or the male pins shown that can be soldered onto proto boards and printed circuit boards. These make perfectly fine connectors, but they're not keyed. You can flip them in any way you want, and they don't lock in. They can be pulled out easily. If you want something a bit that solves these problems, look at JST connectors. That's an industrial brand name. This is one of many families of small plastic keyed connectors, meaning they can only be plugged in one way, and they typically have some kind of plastic lock or snap to prevent them from yanking out easily. A simple form of raw wire termination, if you just want to take a piece of metal and connect it to a circuit, you can look at screw terminals. These are things where you lay the bare wire in, you screw a screw down on top of it, and it crunches down on that wire, connecting it to the metal of the terminal. So you can find these in a form factor that goes into a printed circuit board or a proto board, as well as standalone ones for hooking up big, what are called power buses. If you have lots of current that needs to get all hooked together, lots of wires need to all be one thing, you can screw them down into one screw terminal. For getting power into a project, a good choice is the barrel jack. You've seen these before, most likely. These are the round connectors with a hole in the middle that plug into a pin into various consumer electronic devices. The good news is these are so common you can find every form factor you can imagine. There's ones designed to go into printed circuit boards. There's panel mount ones, so if you make a box enclosure, it can have a nice professional looking port for a barrel jack on the outside. You can get solder ones where you solder raw wires onto it and then put a boot on the back and it looks like a professional wire. You can get screw down ones for quick prototyping or field work where you lay raw wire, screw it down, and it turns it into either a male or female barrel jack. And any DC adapter that you might plug into the wall will often terminate in a barrel jack. There's one really common size you can find easily online. That's the 2.1 millimeter, 5.5 millimeter one. This is what's on an Arduino, and any kind of hobbyist DC adapter you find will typically be that one size. If you want to have a lot of wires, up to 8 wires, get into a project easily and be disconnectable, you can reuse a really common connector in the world, and that is the RJ45 jack. This is the kind of connector they use for wired Ethernet. You might find one on your home internet router. You can get the connectors, the raw wire, and a tool that lets you crunch them together to make custom wires of any length you want to make your own cable. And you can find female ports of this that can go into proto boards and breadboards and so on. This way you can use a common, off-the-shelf, cheap kind of cable that gives you a lot of conductors that are color-coded to any length that you want. It's a real shortcut. Now, probably the most important topic I can talk about in the context of physical wiring is strain relief. Strain relief is essential, and it is the most commonly overlooked aspect of electronics design. Strain relief is mechanical support for an electrical connection because the actual solder or whatever connection you make is not that strong. It'll break, it's brittle. There's many forms of strain relief. So if you look at any cable you find around there, there's probably a little flexi bit right behind the end of the cable. That boot is a form of strain relief. So if you bend that cable back and forth, that boot takes a large amount of the force out of it. If you have a wire coming out of a box that you've designed, you might zip tie it or cable tie it to something in that box so that if you yank on that cable, you're pulling on a zip tie instead of pulling on a solder joint. You might take a hot glue gun and kind of blorp around a series of solder connections you've made. So if you yank on it, you're pulling on hot glue and not on the solder. You might use heat shrink tube that you place around a connection. You hit it with a heat gun, which is like a super hair dryer. The tube, because of its chemical properties, will shrink up and hold tight that connection. So if you again pull on the cable, you're actually pulling on a heat shrink tube instead of your solder connection. Strain relief isn't optional. I've seen so many projects that look totally great, everything's wonderful, then you bend one thing, a wire breaks off, and it's broken. Don't skip your strain relief. It's going to bite you. Okay, now, you've got your prototype. You've messed with electronics. You've figured out your sensors, your actuators. You've hooked it up. You've got good wiring techniques. Now it's time to kind of bring it all together because it's presently a pile of stuff on a desk, and you want it to become some kind of box or robot or unit. It's time to design the structural aspect of this. So I'm going to give you just a smidge of mechanical engineering and design, just enough to get going thinking about how to fabricate the physical aspect of your project. If you're making something in the real world, one common way of thinking is with two ingredients, beams and sheets. So for beams, think of them as basically some kind of stick. So a lumber in the form of a 2x4 beam, common board, which is a flat chunk of lumber, pipe, so PVC plastic or metal pipe. You can get aluminum or steel or plastic in the form of rods and tubes and L channels and flat bar and C channels. There's all kinds of beams you can get in that context from metal sellers. There's even something called aluminum extrusion T-slot, commonly called 80-20. You can combine with nuts and kind of Lego your way through it. You can think of beams as a way to frame, make a skeleton for your device. The other ingredient to think about is sheets, flat two-dimensional planes of material you could use to design with. Plywood, giant like 4-foot by 8-foot sheets of plywood. Plastic in the form of either acrylic or ABS or polycarbonate are all materials you can readily get in flat sheet form. There's also sheet metal, aluminum or steel that can be bent and formed into shape. So when you're designing things, you could think, for instance, I will frame this using beams, for instance, maybe 2x4s, and I will cover it. I'll make these skin out of sheets of, let's say, plywood, and you just designed a barn. If you take 80-20 aluminum and use these fasteners and gussets and things to make a frame, and then put acrylic plates on each side, you've made like a nice enclosure for like a 3D printer or something. So beams and sheets, you could use these kind of mental models as you go about putting together the design for your device or machine. So let's say you're making a mechanism. It's some kind of robotic mechanism, and it's going to pick up balls or shoot something or close a claw, that kind of thing. One way to think of it is you'll probably have important actuators, motors that need to do something and be in certain orientation. Let's say 2 wheels will take in a ball or something. Imagine those floating in space, exactly where they need to be to do the job, and then add whatever beams or sheets you need to hold them there. So you work backwards from your essential actuators back to the frame that's needed to support them. So let's say you do this, you build your frame, and it's just too wobbly. All your joints are just flopping around. It's not strong enough. It's breaking. Here's probably the number one highlight from the field of mechanical engineering. Use triangles. Triangles make joints strong. So you see in the picture that the little guy's sad because his beam is bending inward. 2 ways to fix that. I might think in sheets and cut a triangle of material that I then fasten to the side of that. That's called a gusset. Or I might make a beam and cut it at 45 degrees on each side and put it in the middle there to make a triangular support or strut that can hold that angle. If you take whatever you build and coat it with triangles, it'll probably be strong. That's good enough for 80% of the things you might want to build. Now, how do you attach these beams together? How do I attach stuff to other stuff? You're going to want to reach for fasteners. Fasteners are things like screws, staples, and so on. They're generally want to reach for before you reach for adhesives. Most new engineers, they think, oh, I want this to be stuck to that. They just want to like glue it there because glue is easy to think about. Glue has a lot of drawbacks. It's hard to unglue things, and glue is often not strong enough. So if you have the option, reach for fasteners, especially screws. Screws come in 2 main flavors. Your wood screws have really big, coarse, bitey threads. to chew into the material to hold them. In the US, they're typically measured by their, quote, number, such as a number 4 screw, a number 6 screw. Just to give you a rough intuition, number 4 is like a little small guy. Number 6 is kind of small for maybe like a handheld machine or something. Number 8 is like a decent size, and number 10 is like a honkin' bigger screw in the context of wood screws. You also have, in contrast to this, machine screws, totally different flavor. These have fine threads because they're not designed to bite and chew material. They're designed to mate with the same precision threads in a nut or other female hole. So the screws will thread into the corresponding nut or other port. In the US, there's two main standards because the US always has bad standards. You have, again, the number system, except now it's being applied to machine screws. Number 4 is small, number 10 is kind of pretty big. But you also have, once you get past the, quote, number 10 size screw, it switches to diameter. You might have a 1/4 inch bolt, diameter bolt, or a 3/8 inch diameter bolt. For either of these standards, either number 6 screw or number 4 bolt, there'll be another number that tells you the threads per inch. So you might reach for a 832. 8-32. That means a number 8 diameter, 32 threads per inch. Or a 1/4 20 is a really, really common bolt. That's a 1/4 inch diameter, 20 threads per inch. You don't have to sweat the numbers too much. Just know that they gotta match. If you buy this kind of bolt, you gotta buy the same kind of nut. Metric has a similar kind of thing, except it's better. It's just M and then a number of millimeters of diameter. So an M3 screw has a diameter of 3 millimeters. It is also followed by a measure of the thread thickness, but you typically don't have to worry about that as much in metric land. If this all sounds like a lot, I'll give you the short version. If you're making a big wooden thing out of 2x4s and plywood, use number 8, number 10 screws. I recommend deck screws. You buy these at a home store. They come in a big tub, and they have what's called a T25 drive head. Now, what is that? Don't freak out. There's lots of kinds of heads to these fasteners. The most common you might see is a Phillips head. That's the little plus sign guy. You use a Phillips screwdriver on that. Phillips screwdrivers are bad. So I'm sorry no one told you this. They're designed to strip out because when they were designed, it was easier to have the screw strip out than to ruin your tool. In the modern era, they are really frustrating to work with. So if you have a choice, go with anything that's not Phillips. So the T25 stands for Torx 25. It's a little star pattern. It's not that bad. When you buy a tub of screws, it comes with a bit that will drive them that you put in your drill or hand driver or whatever you're doing. If you have a little tiny thing you're building, like a little robot or machine fits in your hand, look at your metric M3 screw or your US number 6 machine screw. You get that and the corresponding bolts, you'll have a good time. There's a whole universe of fasteners out there, but that's enough to get going. 2 more quick tips on fasteners. If you're designing something to be 3D printed that you're going to use fasteners in, so for example, to put the cover onto an enclosure box, consider what's called countersinking. This is an option in most 3D packages that basically says, carve out the shape of the head of the screw so that the screw sits flush with the top. It's not a big deal, but if you do it right, it looks so professional. The other thing you can do is what are called nut traps. So you place a hole in your design, the size and shape of a metal nut, and install a metal nut in your plastic 3D printed thing, so that when you put in a screw on the other side, it bites into the nut instead of biting into just plastic. It makes for a stronger connection, and it's pretty easy and cheap to do. If you want to dig deeper into the whole world of fasteners, there's a link there, Introduction to Fasteners, and it's a whole universe to be explored. So let's say you found a situation where screws aren't the perfect choice. Here's 3 other good things to put in your brain. Hot glue. Hot glue is the prototyper's best friend. Heats up, it's cheap, heats up quick, glues things together, and it dries non-sticky. So you can use it as not just a glue, but also as a reinforcer, a way to do strain relief, an electrical insulator. It's really useful stuff. You try to get far in this area without using zip ties or cable ties. These are typically little nylon guys. You wrap them around something, you cinch them tight, they don't back up. You can use them for holding cables together, holding entire robots together. Zip ties are fantastic. I use them all the time. If you come up with a situation where zip tie is not strong enough, they make stainless steel zip ties. You can get these at any home store, and those things are good at 50 pounds. So zip ties are very versatile, good things to have in your plate. Last thing I'll point out is gaffer tape. Gaffer tape is a cloth back tape with adhesive formulated to not turn into goop, not dry out quickly. It's reusable, and if you get a lighter color like white, you can even write on it to make labels. It's good for anything that's temporary or semi-permanent. Think of it as like duct tape, but better. A lot of people may say like, oh, duct tape for engineers. Duct tape for kind of engineers. Gaffer tape is the duct tape for real adults. So let's move into digital fabrication. Before I get too deep into this, I want to point out that analog fabrication is great. So before you get fixated on your 3D printers and lasers we're going to be talking about, don't forget that it's really easy to cut a chunk of wood, cut a chunk of metal, cut a chunk of plastic, put things together with your hands. It's often faster than digital techniques. So don't automatically pivot to your digital fabrication techniques. The basic traditional methods of building are not that hard to learn, very powerful, and oftentimes faster. That said, digital fabrication is fantastic. You can design something in your 3D software and have it exist in the real world without having to whittle it out of a block of material yourself. The most common entry-level thing people get into in the field of digital fabrication is 3D printing, where you design something in a 3D computer-aided design package and ask the 3D printer to squirt it out of plastic. Getting into 3D printing, there's a bit of learning curve in terms of not every model will print equally well. There's techniques as how to design for 3D printing. They're not super crazy, but I invite you to research this as you dig deeper into the topic. If you're here on Duke's campus, I recommend, if you haven't already, visit the Duke CoLab. They have a wall of 3D printers like that's shown here, and it's a really fantastic way to get into this method of fabrication. Using 3D printing, you make a variety of plastic things with low to moderate amounts of mechanical strength. Another useful thing to have in your toolkit is the laser cutter, if you have access to one of these. A laser cutter can cut a 2D path into a wide variety of flat stock materials, such as plastic, 1/4-inch plywood, and so on. This is great in general, but especially for panel mount components. If you get your sheet of clear, professional-looking acrylic and you have a laser cut all the holes for your various panel mount components and you snap them all in place and screw them all in place, you're going to wind up with a really great-looking, professional-looking interface. One minor tip on this: if you're dealing with plywood as your material and you have a charring or smoking on the edges, throw some masking tape on that wood first before you laser it. It'll clear those right up. Using laser cutting, you can make full chassis, full devices. In the example shown here, I've cut out a series of back, a series of middles, and a front that were then glued together and combined to form a case of this small electronic toy. Moving further with digital fabrication, you can look at using CNC mills. That stands for computer numerical control. It basically means robot-controlled cutting machines. So there's multiple CNC machines here at the Duke CoLab. These allow you to cut thicker materials with more complex geometries. So if you want to cut something out of thicker wood, if you want to cut a relief or a complex shape, CNCs can help you do this. It's definitely more complicated than either of the two previous techniques, but offers a wider variety of possibilities. Lastly, I'll point out, if you are fortunate enough to have access to it, a water jet cutter is a really fantastic tool. Think of it as a super laser cutter. The laser cutter typically will only do plastics, 1/4-inch plywood, relatively light materials. A water jet cutter will shoot a very fine beam of water and, most importantly, a hardened substance like garnet through a material to cut it. This allows it to cut things made of aluminum or steel. So if you want to make gears, fabricate gears or something heavy and strong out of steel or aluminum, a water jet cutter can help you do this. If you're here on Duke's campus, the Duke CoLab does have access to a water jet cutter machine. With that, I want to thank you for riding along with me on this journey. We've now covered everything: sensors, digital modules, and actuators in the first video. And in this video, connectivity and control, the human interface, and designing the physical enclosure or chassis for your device. Obviously, you probably have a lot of questions on where to go next. I invite you to click on some of the links and tutorials that I included, as well as do your own research as you explore the possibilities in your own design space.